Hello everyone, Dr. Zia Tahir here. This video tutorial is solution of problem 2.73 of chapter 2, free vibration of single degree of freedom system from Mechanical Vibrations book, 5th edition by S.S. Rao. Statement of the problem is a uniform slender rod of mass m and length L is hinged at point A, so that is hinged at point A, and it is attached to four linear springs and one torsional spring. So these are the four linear springs and one torsional spring, as shown in figure 2.96. Find the natural frequency of the system if K is equal to 2000 Newton per meter, KT is 1000 Newton meter per radian, M is equal to 10 kg, and L is 5 meter. So to solve this problem, we need to select first a coordinate system. And here, most appropriate is rotational coordinate system we need to select. So first I'm going to draw its free body diagram, and then from that free body diagram, I'll show all those forces. So let's say that is the center of mass of the rod, which is from here it is L by 2, and from point A, the distance between the point A and G is 2L over 3 minus L over 2, which comes as L by 6. So I am assuming that the rod has a that is the direction of rotation of rod, and an angle theta is given to it. So the assumption about angle theta is, so theta is small. So theta is small in radian. So sine theta is nearly equal to theta, and cosine theta is equal to 1 for this case. Now, now with the top end of the rod is moving towards right, so this K spring is being compressed. So let's say for the rod, its distance is x1. So then this spring on the top right, so it is going to apply a force which is kx1, and then K2, it is being stretched or extended. So then it will try to compress that spring. So it is Kx1, the both forces. And similarly, the bottom end of the rod is moving towards left. So let's say its displacement is x2. So then the restoring force from this K1 will be the left spring. It is Kx2 and then Kx2. Then this spring Kt, torsional spring. So torsional spring will resist in at that point A, somewhere here, in opposite direction of motion. So here the direction is taken in clockwise. So at point A, so the restoring or spring force will be Kt into theta, and this will be opposite to the direction of rotation, and because assumed direction of motion is clockwise, so it must be opposite to that. And then another force is being acting here, so which is due to weight of the rod, and that is mg. Okay, so weight mg, and it can be resolved into two components. One perpendicular to the rod, which is mg sine theta, and one parallel to the rod, which is mg cosine theta. As mg cosine theta is passing through the point of rotation A, so it is not contributing any moment, so mg sine theta will contribute. And based on assumption, sine theta is nearly equal to theta, so it is mg theta. Now that x1 is equal to using here s equal r theta relationship, s equal to r theta, so x1 will be a third L, that is the radius of rotation of the top, into theta, and for the lower end, its linear displacement is x2, which is 2L over 3 into theta. So now Newton's second law of motion can be applied here in rotational direction, which says that sigma sum of all moments is equal to J equivalent theta double dot. So sum of all moments, so these two forces can be combined, and so now these kx1, kx2, they can be combined, and similarly kx2 and kx2 can be combined, but they are in horizontal direction, and their components are required which are perpendicular to the rod, and those components perpendicular to the rod is kx1 cos theta. And as we assumed that cos theta is nearly equal to 1, so then the component perpendicular to the rod, they will be kx1, and similarly for all other forces, their components are kx1 or kx2. So then sum of moments, so, so these two forces, their moments times by radius of rotation for that point, it is L over 3. And then for these two forces, multiplied with 2L over 3, and then mg sine theta, and the distance between G and A is L over 6, and then kt theta, so that is fourth moment. So there are four moments which are opposite to the direction of motion, so all will be negative, and sum of all those forces is equal to J equivalent theta. So these four moments, the first one is minus kt theta, then these two forces combined, it will become 2kx1 times by the radius of rotation, which is L over 3, and then these two forces on the bottom, kx2 plus kx2 combined, so 2kx2, and then radius of rotation for the bottom till point A is 2L over 3, and then the component of weight is mg theta times by the distance between A and B is L over 6, and equal to J equivalent. Now, this rod is not rotating about its center of mass. So when it's not being rotating, so then we will use that the moment of inertia of a mass m having a center of mass rotating about point A, and distance between A and G is d, so it will be Ga as Jg plus md square. And for the moment of inertia of rod having mass m, length L about its center of mass, so it is Jg is equal to 1 over 12 ml squared. So it will be now 1 over 12 ml squared plus md squared. M and d is the distance between A and G, which is L over 6 squared is equal to theta double dot. So now after substituting value of x1, x2, this can be simplified. So it can be simplified as Here, x is a third L theta. If you're going to substitute here a third L theta, so then a third times a third, it will become 1 over 9 times by 2 is minus 2 over 9. L times L is L squared theta. Now here x2 is 2 third. So 2 third times by 2 third, it will be 4 over 9 times by 2 is 8 over 9 k L squared theta. And then 1 over 6 mg theta L is equal to, this will become 1 over 12. And from here, after squaring it, it will become 1 over 36. So 1 over 12 plus 1 over 36, it is 1 over 9 ml square theta double dot. So then it can be simplified as, if I take all those terms on the other side, and it minus 2 over 9 minus 8 over 9, it will become 10 over 9. So 1 over 9 ml squared theta double dot plus kt theta, and minus 2 over 9 minus 8 over 9 is 10 over 9 k L squared theta plus 1 over 6 mg theta L. So now I can get rid of denominator by multiplying all terms by 6 on left hand side and right hand side. So it will become ml squared theta double dot plus 9 kt plus 10 k L squared plus 3 over 2 mgl into theta. So that is now equation of motion. And if we have like for translational, uh, for rotational motion, so we have J equivalent theta double dot plus kt theta. And for this type of expression, we have omega n is equal to kt over J equivalent. So it means that whatever is the coefficient, whatever are the term with theta, coefficient with theta, and then theta double dot, so that will give natural frequency. So the natural frequency here is 9 kt plus 10 kl squared plus 3 by 2 mgl over ml squared. So that is the expression for natural frequency. And then all the values are given there. K is equal to 2000, kt is equal to 1000, m is 10 kg, and L is equal to 5 meter. So these value can be substituted in this expression. So after substituting value K, kt, m, and L in the expression, so natural frequency is 45.1547 radian per second, and that is the solution of this problem. So thank you very much for watching.